Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working in a new chapter, Chapter 5, of the Elementary Principles of Chemical Processes, 3rd edition book. Okay. Problem number 5.1 says a liquid mixture containing 40 weight percent N-octane and the balance N-decane flows into a tank mounted on a balance. The mass in kilograms indicated by the scale is plotted against time. The data fall on a straight line that passes through the points t equals 3 minutes, m equals 150 kilograms, and t equals 10 minutes, m equals 250 kilograms. Part A, estimate the volumetric flow rate of the liquid mixture. So we've got 40 weight percent octane going in. I think I normally use this. Yeah, 40 weight percent octane going in, 60 weight percent decane going in. Okay. We need to know what the flow rate is. We're going to estimate that by using our balance. This is our mass measurement. The mass measurement is a function of time. That's what this means. Mass of tank equals time. Okay? Or is a function of time, not equals time. Okay, so yeah, it's flowing in here, and the tank level is increasing with time. Okay, important to know that they gave us mass, and in part A they asked us what is the volumetric flow rate. So not the mass flow rate, what is the volumetric flow rate? So if we're all working in masses and we need to convert into volume, then we need to know the density. Well, this is the density of a mixture. Okay, so how do you get the density of a mixture? One way to do that, well, the only real way to do that is to measure it. You have to do it empirically, find out what the density of the mixture is. There are some models you can use that can help you estimate what the density of a mixture is, and it really helps if the solution behaves ideally. It makes it easier to calculate, or at least some of our methods are going to be more accurate. Okay, so one method for estimating the density of a mixture is to take the inverse of the density. This is the density of the mixture, and these are the densities of the components. And if you do the inverse of those, then you're averaging the molar volumes, which is a pretty good estimation for what ideal mixtures follow. Okay. And in this case, octane and decane are both straight chain organic molecules. They're nearly identical, and so they behave very similarly. So this is the thing that we're going to use in order to combine those. So in this case, we're going to use this equation to estimate the density of the solution. This is the mass of our tank. They said it falls on a straight line, so I wrote this is the equation of a line. Our slope is m, b is our intercept, and t is time. So now we need to solve the equation of the line. We need to know what m and b are. Okay, so the mass of the tank at time 3 is equal to 150 kilograms. So we put 3 in here and 150 there. Then we have mass of tank 10 minutes equals 250 kilograms. Then we say 10 for t and 250. Okay, now we have 2 equations and 2 unknowns. Very easy to solve. This is the answer to that equation. So now we have our slope and our intercept. This is our equation for how the mass of the tank changes with time. Okay, we want to know the mass flow rate so that we can convert the mass flow rate into a volumetric flow rate. So our mass flow rate is equal to what is the change of the tank mass with time, okay? So the change of the tank mass with the change in time is equal to the slope, okay? Now we need to know, now we're going to use our equation in order to calculate what the solution density is so that we can convert this into a volumetric flow rate. Okay, so we use our equation here. We need to know what the component densities are, and we just look those up in the back of the book, and these are the component densities. I'm going to do it in kilograms since they gave us all of our other things in kilograms, so kilograms and meters cubed, okay? And they have the same density according to the back of the book. So that makes combining these a lot easier, right? So and this isn't always true. This isn't always true. It's only if the solution behaves ideally, right? So if they behave ideally, then when you combine them, they will have basically the same volume, which is pretty much true for this solution because they should behave ideally since the molecules are nearly identical, okay? So now we use our solution volume. We've got our mass flow rate, we have our solution density, so now we calculate our solution volume, okay? So this is our solution volume, our volumetric flow rate, okay? Part B, what does the empty tank weigh? Okay, so they didn't tell us if anything was in the tank before the time started, but if you assume that the tank is empty when the time starts, then the intercept of this line equation will be what the tank mass is, okay? So if the tank is empty at time equals 0, then we just say T equals 0, so that goes to 0, and we're just left with 107, right? So 107 kilograms is the mass of the tank. Okay? That is it for problem number 5.1. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.